Here listen. This is a beam of length L is supported at the ends and carries a concentrated load W at a distance A from each end. Find the slope at each end and under each load. Find also the deflection under each load and at the center. The figure 6.42a, this this figure shows a beam span of length L carrying point loads W each at D and E distant A from the supports. Figure 6.42b shows the bending moment diagram for the beam. This one. Figure 6.4c shows the conjugate beam carrying load corresponding to M by EI diagram. The M by EI diagram is practically the same as the M diagram, except in the case of the M by EI diagram, we should imagine a thickness of 1 by EI. For example, in this case, where W A where W VB is equal to W, V is equal to W, A, D, C, E, B, length L, given beam. Bending moment diagram. A, D, E, B, WA, WA. VA is equal to WA into L minus A over 2EI, conjugate beam, 1 by EI. VB is equal to WA L minus A by 2EI L. Note, in conjugate beam maybe have the same shape as the bending moment diagram. Total load on the conjugate beam is equal to volume of the load diagram is equal to 2 into half A into WA into 1 by EI plus L minus 2A into WA into 1 by EI is equal to how here half A into WA into 1 by EI. This can be due to this one. This is the volume of the load diagram, total load on the conjugate beam. This one is the conjugate beam, and here in this case, for example, here is WA A, then 1 by EI, half A plus L minus 2A into WA into 1 by EI. Note, this is area under curve, half A into WA. This one is A, this is WA. So this is the area under the curve. Now, here answer came is WA square by EI plus WA into L minus 2A by EI is equal to WA into L minus A over EI. Therefore, reaction at each port for the conjugate beam is equal to half the total load is equal to WA into L minus A over 2I. Slope at each end of the given beam is equal to shear force at each end of the conjugate beam is equal to WA into L minus A over 2EI. Slope under each load of the given beam is equal to shear force under each load of the conjugate beam, which is equal to WA into L minus A over 2EI minus half into A into WA into 1 by EI. Here, note here, y here is WA into L minus A by 2I, y here is minus half into WA into 1 by EI. Here listen, here WA into L minus 2 by EI forms clockwise direction, where half WA into WA into 1 by EI forms anti-clockwise direction. That's why. Then WA into L minus A by 2EI minus WA square by 2EI plus which is equal to WA into L minus 2A divided by 2EI. Deflection under each load of the given beam is equal to bending moment under each load of the conjugate beam is equal to WA into L minus A divided by 2EI into A minus half A into WA into 1 by EI into A by 3. Why here A by 3? Since it is a centroid, it is the distance from here to here. Here the centroid, here it is the distance A by 3. Then WA square into L minus A by 2EI minus WAQ by 6EI is equal to WA square by 6EI into 3L minus 3A minus A, which is equal to WA square into 3L minus 4A divided by 6EI. Deflection at the center of the given beam is equal to bending moment at the center of the conjugate beam, which is equal to WA into L minus A divided by 2I into L by 2. Since in this diagram, this distance is L by 2 from the center. From this end to A end to the center is the distance L by 2. Minus half A into WA into 1 by EI is equal to L by 2 minus 2 by 3A, where 2 by 3A is this distance. We get L by 2 minus 2 by 3A. Minus L minus 2A divided by 2 into WA by EI into L minus 2A divided by 4. This is L minus 2A. Then this is L minus 2A. Then from the center, this is L minus 2A by 2. From the center of gravity, then L minus 2A by 4. We can get the answer WA into L minus 8 by 4 EI into WA square by 12 EI into 3L minus 4A minus WA into L minus 2A whole square over 8 EI is equal to W by 24 EI into 6L into L minus A minus 2A into 3L minus 4A minus 3 dash. Then we get the answer WA over 24 EI into 3L square minus 4A square. Hey, see here. This is arch. It depends as the curved beam in the vertical plane in which the horizontal movement at a spot is totally prevented, and as the crushing wall will be induced at this spot. This is W per unit meter. This is A, this is RA, this is X, this is R, this is H. Mx is equal to RA into X. Mx is equal to RA into X minus Wx square by 2 minus H into Y. Minus H into Y. Since it makes the concavity downward. For concavity downward, the bending moment is negative, so concavity upward, making the bending moment is positive. Mx dash is equal to W into X square by 2. Here, see here. This is RA, this is X, this is W per unit meter. This is Mx is equal to RA into X minus W X square by 2. Arch is defined beams first transfer the applied load to end spot by bending moment and shear force. Arch transfer applied load to end spot partly by the axial compression and partly by the flexure. Beam. The stress are maximum at few points and the material in most of the portion is understressed, is unutilized. Arch. Axial compression, which is at predominant force, and every particle of the cross section of each of arch structure have equal stress. Here, see here. This can be the arch. In arch, wherever the compression force is there, the material is fully utilized. In arch, wherever the compression force is there, the material is fully utilized. Types of arch based on sport condition: 3-inch arch. This is on the 3-inch arch. 2-inch arch, 5th semester. This is the 2-inch arch. Based on geometry or shape: parabolic, circular arch, polygonal arch, elliptical arch, any other curved shape. Fixed arch. This one is fixed arch. This is 1-hinged arch. This is hinged. 4-hinged arch. This is 4-hinged arch. Deficient, unstable, cyclic. This is A, this is B, this is X, this is Y, this is Y, this is YC, this is C. Y is equal to 4YC over L square into X into L minus X. This is equation to the arch. Then is the boundary condition. dy dx is equal to 4YC by L square into L minus 2X. At X is equal to L by 2, dy dx is equal to 0. At X is equal to 0, comma Y is equal to 0. Internal force in arch. Normal stress, radial shear. This is Nx, this is M, this is theta, this is H, this is Qx. this one is can be the normal stress, this can be the shear stress. This can be the normal stress, this can be radial shear. Nx is equal to H cos theta plus V sin theta. Qx is equal to V cos theta minus H sin theta.